Alright, this video is the second half of our discussion of Chapter 6 in Openstax Astronomy, where we talk a little bit more about the details of telescopes beyond the fact that there are reflecting and refracting telescopes. That was the previous video. So when we build a telescope, there's a couple of aspects that we have in mind when we build it. So the first one is what kind of electromagnetic radiation it can detect. So again, from Chapter 5, we talked about these different types of light, and if we're building a telescope on the ground, that means we can only build radio telescopes or visible light telescopes. Then when we're building something, we want to decide whether it was out of lenses, primary lenses, or mirrors. So a backyard telescope, you can actually still buy either type. But if we're building a large astronomical scientific observatory, it's going to be mirrors moving forward. We talked about that aspect in the previous Chapter 6 video. Then one of the other things we talked about is how the telescope gets light to the instruments or to the detectors, or if you're actually looking through the telescope at an object, how it gets that light to the eyepiece. And that's when we have those different ways of getting the light out of the telescope tube, the prime focus, the Newtonian focus, Cassegrain. We don't need to know those details, but if you're researching a telescope, for example, that might be something that you're looking at and deciding between. And then one of the most important aspects of a telescope is how big is that telescope. Now, given unlimited funding, we would build as big as we're physically capable of building. And we'll talk about why bigger is always better for these telescopes. Bigger feeds into all of the three main telescope powers, which we're going to go through now. So when we have a telescope that's smaller or bigger, the only major difference is cost. It is more expensive to properly machine a larger lens or a larger mirror than it is for a smaller one. Okay, so there's three main powers for a telescope, and we do need to know all three of these. So the first is light gathering power, and we talked about this briefly in the previous video, that when we think about Galileo with his kind of spyglass kind of telescopes, the reason that they still allowed him to do groundbreaking astronomy is because they were wider across than his eye. The bigger a telescope is across, the more light we can gather, and this power allows us to see fainter objects, dimmer objects that we would have missed otherwise. So bigger across, the more light we receive, and that is better for seeing faint or dim objects. The second power is resolving power. This one's a little bit difficult to talk about without going into more of the physics and behind light and the optics and some of the more complex stuff that we really don't have time to touch on in this course. But the idea here is the two images on our slides represent a pair of stars that are very close together. And on the left, if we don't have good resolving power, the sort of ring-like shape that we're seeing here is based on the way that light works when we're trying to zoom in on a very particular small source. And we can't actually tell the difference between the two very close nearby points of light. We aren't able to distinguish that smaller detail. Whereas on the right side, we're actually able to tell that there are two distinct point sources directly next to each other. Even though it still kind of looks like they're blobbed together, we can at least tell that they're separated. And that's because we can see smaller detail. There's an equation that we won't talk about, but for resolving power, the bigger diameter your mirror or lens is, then the better resolution you have, the sort of smaller the details are that you can see. So the key thing here is that first sentence, resolving power is the ability to separate close by objects or to see very small details. For example, tiny craters on the moon if you had a telescope looking at the moon. Now, resolving power is limited by the Earth's atmosphere. No matter how good our telescope is, and no matter how big it is across, The fact that we're looking through all of that air between us and space means that even the smallest details, that light can get jostled enough by the air itself, that we can't distinguish those small details. The amount of light coming down is going to be the same, which is why light gathering isn't actually affected by the atmosphere in the same way, but resolving is. There's a word that's going to come up often enough that we need to understand it, seeing. And when an astronomer talks about the seeing at a particular location or the seeing on a particular night, what they're talking about is the atmosphere imposed limit on the small detail structure that they can see, which might be worse than what the telescope and the equation involving the telescope would tell us it is. So if we put our optical telescopes, our visible light telescopes on top of mountains, there's physically less air between us and space, and that is a major improvement to the seeing. And then the third power for telescopes is magnifying power. This is useful if you're doing backyard astronomy and have, for example, the planets or the planets in our solar system and their moons, or if you're looking at our moon itself, kind of zooming in on details is going to be based on the size of your telescope and the particular eyepiece that you're using. This is not nearly as important for large-scale scientific astronomy as the other two factors. So it's the least important of the three powers of telescopes. It's still useful. This equation here, we're not going to ever see again, but the magnifying power, P with a little subscript M, is based on the focal length of your primary compared to the focal length of your eyepiece. So you can zoom in on an image, but the key thing, the reason why this is the least important, is because if you zoom in on a blurry image, it will stay blurry. Or if you zoom in on an image that can't see faint things, you can't all of a sudden see those faint things if they weren't in the original image. The idea of zoom and enhance on TV shows is purely fiction. If you have a blurry image, zooming in on it will not make it all of a sudden a better image. Now, besides the powers of those telescopes, and again, I went through those kind of quickly because the slides that are posted to Blackboard have all of that text for you, and you can rewatch the video if you want to, or pause if you need to. But the next thing to consider for telescopes is where we want to build them. Now, there's a couple of things to consider when we're building a telescope. We want good weather. So no one is going to build a fancy, expensive, giant astronomical telescope here in Grand Rapids because it's cloudy quite often and it snows a lot. When we're building a telescope, we want a really dry site, one that doesn't get precipitation of any kind very often and that has clear skies most of the days of the year. Deserts are a pretty good place for that. Seeing, we just talked about the resolving power or resolution power. That limit is based on how much air you have to look through, so we want to put our telescopes, especially the visible light ones that have a bigger issue with this seeing, we want to put those visible light telescopes on top of mountains. So mountains in dry sites are great. And then city lights are a major issue. We're going to see a couple of example slides that show us the difference between if we're near a city and if we're not, or if we have lights around us, light pollution or not. We want to put these things, we want to put big telescopes in remote locations where there's not a lot of people around, not a lot of lights around. So one of the ways that we can improve the resolution limit or improve the seeing, besides putting them on top of mountains, is to have telescopes use adaptive optics. Now, the actual process of adaptive optics, if you're curious, you can find internet resources if you search it. We don't need to go into those details, which is why I'm not going to present particular links for that. But the idea is a computer is constantly adjusting the particular shape of the mirror of the telescope to make the image as clear as possible. Often the way this is done is that the telescope actually shoots a laser into the sky. Sounds awesome, right? shoots a laser into the sky, and that's part of the image, but then they can see the particular shape that the laser point has in that image, and any distortions are being caused by the air, and so we can kind of adjust for that as we go. There's a lot more detail to it that we're glossing over because we don't need that detail, but you're welcome to look into it more. Or if you're researching a telescope that has adaptive optics, we at least have kind of heard what that is. But again, getting back to that list of weather's obvious enough. Seeing, we're starting to understand through this video. But the biggest issue that confronts modern astronomy, especially as we move forward in time, is light pollution. Now, the images on our slide here are from the year 2004, where there was a major blackout in Canada and the New England area, so the northeastern United States. On the left, we have what the power grid looked like from space. These are images taken from space at the United States. And first of all, we notice that even back in 2004, there is so much light pollution. All of this light is just leaking out into space that we can actually tell where the Great Lakes are. We can tell that this big ginormous blob here is Chicago. Like, we can pick out all the major cities because of the light that is being produced. And if it's light that's escaping up into space, that's not actually being useful light for those cities, and it is simply polluting the skies from being able to have nice views of the stars for everyday people, which is a right that all people should have, and a lot of people don't have access to clear skies. But it's also a waste of electricity, and in a time when we have to be so careful with our resources, all of this light escaping up into space means it's not actually doing what it's supposed to, and it's wasting electricity. But if we look at where that blackout was in that year, in that summer, the power was out for several days, and we can see that it just kind of looks like someone took Photoshop and just covered it in black. All of those lights from those cities are just gone. And the difference is staggering when you look at what the skies were like for people on a normal day. So all of this weird orangey yellow glow. For the most part, that weird orangey yellow glow is coming from the fact that a lot of our outdoor lights use the gas sodium. So we talked about emission spectra, and sodium lamps are basically filled with sodium gas, and they make that kind of weird orangey yellow dystopia kind of color. That reflects off the light. It doesn't even need to be cloudy to see this. It reflects off the air. It doesn't even need to be cloudy to have light pollution exist. And then on the right is that same area during that major 2004 blackout, and just what the skies look like instead at that time of year. And it really is impressive in a kind of sad way, the difference between what we should have access to and what we actually have. Now, certainly this image, it's showing part of the Milky Way, and a lot of students have never seen the Milky Way in their whole lives. And it is true that this image is a photograph that's longer exposure. It's showing us more than our eyes would actually see in that site. But the exposure length was the same for both of these, and so the difference is still going to be staggering, even if you're outside at night looking at the skies. This really is the biggest issue for modern astronomy, is light pollution. The book lists a lot of telescopes in this chapter, and this kind of is the end of section 6.1 of the chapter. And we're just going to do some brief highlights of everything else. There is a lot to discover with telescopes that I really want us to kind of discover on our own as we're researching a telescope, and not having me tell you all these things that aren't as important to the big picture. So we'll go through just a couple more key ideas. So the first thing is telescopes can gather light to make images, But as we talked about in chapter 5, astronomers, for most of their effort, are actually looking at spectra. For most of their research, they're actually looking at spectra instead of images. Images give us a nice overall view of what's happening in that part of the sky, but the spectrum taken from a star or other object allows us to actually think about the physics of what's happening and what processes are going on with that object. So the study of spectra is called spectroscopy, and you may come across the word spectrometer or spectrograph, and you can review this slide on Blackboard for the definitions of those. Those tend to be older words at this point, now that we have telescopes connected to computers, but it's still something that might come up. The other things that telescopes can do, besides images and besides spectra, both of which are using the electromagnetic spectrum, is that we can use the idea of telescopes to actually measure different things as well. So gravitational waves are not a type of electromagnetic radiation, and it's only been in the past couple of years that we've actually been able to build telescopes to measure gravitational waves. And we'll talk a little bit more about that later on when we get to chapters 24 and that part of the textbook. But gravitational waves are something that is separate from the idea of light. They're actually ripples in the fabric of space-time, which is pretty cool. And we'll talk about those later on. Neutrinos are not in the electromagnetic spectrum, and yet we can use telescopes to detect them and to identify that they have interacted with things. And we'll turn our attention to neutrinos and neutrino telescopes in chapter 16. Not now. And then the final example that I want to mention here, because there's not a better place for it, is that cosmic rays are also not part of the electromagnetic spectrum. Cosmic rays are actually very high energy, fast-moving protons that typically come from outside the solar system, and they can be detected in different ways with the right kinds of instruments. Hello again. You'll notice a scene change, and that's because my computer died last night, 6 slides before the end, but we're back. So the remaining slides that we have left are highlighting a couple more of the advancements that we've made in the last couple of decades. And one of the ways that we've been able to improve mirrored telescopes, so reflective telescopes that use mirrors, is by segmenting the mirrors. Now on the left side of our screen we have a single large curved mirror, the way that we might use for a regular reflecting telescope, and the way that we used for Hubble Space Telescope, for example. The hole in the middle is because that's where the light's shining back through. And underneath it we have an example of a segmented mirror telescope. So with the segmented mirrors we make these sort of hexagons, kind of like a beehive, and they're connected to each other so that each one of those hexagons is exactly the right shape to be part of that overarching curved pattern. But the big advantage is that they can be thinner and each have their own set of computer-controlled thrusters to keep them in place, the right shape, and to be able to allow us to build much larger telescopes than we can physically manufacture a single large mirror for. On the right side of the screen we have a wide array of these segmented mirror telescopes as well as existing regular mirror telescopes, and in the upper left corner we have the very 2 largest refracting telescopes ever used in astronomy. So the Great Paris Exhibition Telescope, which was used for a short period of time, and the Yerkes Observatory, which we had on our slides previously. Now if we look at all of these different examples, we notice a couple of things. First of all, in the background they have a couple of pictures here. One is the overwhelmingly large telescope. Sometimes astronomers are not so great at naming things. that project was canceled. But at the very bottom, you can sort of see part of a curve of Arecibo. And Arecibo is one of these very large radio telescopes that uses an existing, basically, basin or valley in the countryside to build an extremely large radio dish. You can look that up on your own, and recently a new telescope, FAST, the 500-meter across telescope in China was built. Now, one thing to compare is if we follow my cursor, the Hubble Space Telescope here looks kind of small compared to a lot of these, and that's because when we put a telescope up into space, we have to actually get it there, and it is very expensive and very difficult to get large objects up into space. The brand new planned mission, the James Webb Space Telescope, and you can tell that this graphic is a little bit old because it says that it's planned for 2018. It is still a future launch. The telescope itself has been built, but we have to wait for the funding to be able to get it up into space. That is also not all that big compared to some of the other examples on our slide that already exist. But again, we have to limit the size that we can put up into space, and even James Webb is going to be folded up when it's launched and have to unfold like origami. Now, with radio dishes, we don't really use segmented dishes to do the same kind of thing. Instead, one of the ways that we've been able to improve radio telescopes and to make them have the advantages of a larger telescope is actually to have a lot of separate dishes that work together in an array. So a telescope array is one that has multiple separate dishes that are all gathering their type of electromagnetic radiation together, but then through a computer we can connect them and compare what they're seeing with each other in a complicated process known as interferometry. We won't get into the details of that. It is a fairly tough topic to cover. But just being aware that scientists are able to connect smaller dishes together and have them act like they have the resolution of the larger one is our big takeaway here. On the left, we have Green Bank Telescope, one of the larger dishes that we have here in the U.S., and we compare it to the Washington Monument and the Statue of Liberty, and we see that it's pretty big. On the right here, we have what's called the Very Large Array, and it's not even the largest array that we have at this point, but it was one of the first and really well-known ones to do that. If you've ever seen the movie Contact, that's one of the places where the movie was filmed. Now, we can make bigger and better telescopes on the ground, but we'll still have the effects of seeing, so going through the atmosphere, having that resolution limit because of the air, and light pollution, which is becoming a larger and larger issue. In order to get past all of that, we really do need to put a telescope up into space. So for example, Hubble Space Telescope uses mostly visible light, but it has vastly better resolving power than anything that we can build on Earth, no matter how large we build. So this is an image of Hubble in space. And there's lots and lots of different images of it, but one that I'm actually going to bring up in our slides is this image here, and it's called the extreme deep field. There was the deep field, the ultra deep field. This is the extreme deep field. And I'm going to pull up the largest picture of it. So as we're looking, we're scrolling through all of this, and I'm just going to stop right about here. And what I want us to think about is this image that we're looking at, and you could always pull up the image on your own, the link is clickable in the slides, is out of everything that we're seeing here, all the light that Hubble gathered, out of all of these objects that we're looking at, only one of them is a star in our own galaxy, and all the rest of these objects, no matter how small that dot, are separate galaxies outside of the Milky Way that are billions and billions of light years away from us. and we're just getting the small amount of light that has been able to reach us in the time since the universe began. The kinds of scales that we're seeing in this image are ones that we will eventually get to later on in the semester, but I just want to make sure that we understand that images like this couldn't have been made on the ground. The small details that we're seeing here rely on a telescope with very good resolving power, and the light gathering required for this meant that Hubble had to spend time looking at this piece of the sky at several different times over the past couple of decades. So it's basically collecting all of the light from that part of the sky, not all in one sitting, but continually putting some amount of effort into collecting photons from there and recording their positions. And then we end up with something that looks like this. So you can read where we just came from, the link itself. You can read through the press release if you'd like to. I'm going to go back to our slides, though, for now. And the last major point I want to make before we quit for today is that beyond all the other things that we've talked about for telescopes, whether we're building refracting or reflecting, how big we're building them, where we're building them, one of the other reasons that we have to go to space with telescopes is if we want to study something beyond visible light or radio waves, then we need to have telescopes in space. And those different types of light are able to give us different structures, like we saw early on in this video with the sun and the Whirlpool galaxy and all of those different types of light. So keep that in mind. This is where we're going to end the video. These links will be clickable in the uploaded slides, and I'll have them for us to have some discussions about. But one of the things I want to make sure that we recognize, and the link here at the very bottom of the slide can walk us through it, although it's a slightly older website, is that all of the images that we are really familiar with in the public conscious about astronomy, for the most part, a lot of the most famous images came from Hubble, and almost all of them are enhanced color. Not to trick us, but to highlight structures that our eyes would not be able to see because of the limited ability of our eyes to see anything beyond the very, very small range of visible light. So keep that in mind, that the images that we're seeing, the colors have meaning. They do have scientific meaning, but they aren't always going to be the colors our eyes would see if we were looking at that image, especially if it's an image that was taken in the kind of light that our eyes aren't even capable of seeing. Often ultraviolet images are color-coded purple to kind of train ourselves to think about it as being ultraviolet, but our eyes can't see any ultraviolet. We would never be able to take that particular image. So just keep that in mind as you're going through images taken from the telescopes you might be researching or just in general. That's all I've got for you for Chapter 6, and apologies for the scene change.